Welcome everybody to this webinar. Let me start with stating the objective of this webinar. I'm trying to learn you how to efficiently implement discontinuity attributes and specifically the similarity attribute in OpendTect. But I will also go around and mention some other things, some other consideration that's important. So it will not be a straight how-to. Also, a focus here on the purpose of mapping faults. I think it's very important to have an objective in mind, and I will go back to that observation that having a good objective in mind early on is very important for the workflow later in this presentation. And then finally, I will mention, especially at the beginning, some general best practices of working with seismic attributes in general, not only similarity or discontinuity attributes, but also other attributes and even neural networks that will help you going through these kind of workflows. This is kind of an advanced webinar, though I occasionally refer back and go into like very detailed explanations, how-tos of particular steps, but I also will glance over some advanced material pretty quickly. And I realize that some people have to read up on that, so we will send later a follow-up email with additional resources, with links to OpenTect how-tos, and references to principal papers about the subjects we mentioned, not only our own papers, but also the chemical papers that are out there in the literature. So let me start with giving you an idea of what will be the overall flow of this webinar. First I will talk about some general considerations, some high-level thinking about how to do attribute workflows. Then I will zoom in discontinuity attributes and some alternative workflows that you have, because it's also important to realize that discontinuity attributes are not the only solution for mapping faults. And then I will go over the principal workflow, how to get to a good result. Data preconditioning, actually designing, parameterizing the similarity attribute, and then once you have the similarity attribute, potentially attribute or image enhancement filters to make the result even more noise-free or more visually attractive. And then I will shortly mention one particular application of it very briefly, because we're going to run out of time anyway. So let me start with the general considerations. I want to talk a little bit about the difference between pure manual interpretation versus seismic attributes. Talk a little bit about moving to a more holistic approach, considering everything and getting to a systematic workflow that is very important in my mind to get to good results. Mention a little bit about typical quality control criteria. And finally, and that's maybe the most important thing, I want to emphasize how to keep involved in the process, keep thinking about it. So, what is the difference between seismic attributes for fault interpretation and manual mapping? To the left you see an image of manual mapping, and you usually do that by interpreting fault states and then interpolating between them. The advantage of that is that you really get your hands dirty, you dig into the data, and you get to know the data. The disadvantages are obviously it will take you a lot of time, especially if you have complex fault systems where you have younger fault systems cross-cutting older fault systems, and you have to figure that all out. And even if you apply a lot of time in it, you will still end up with a relative simplistic model of your fault system. Usually those faults are modeled as large straight planes, singular planes through your seismic data. Well, the seismic data actually contains a lot more richness in information about faulting. To the right you see a discontinuity attribute that we use there to extract an image of a fault system, and you can already see that there's much more richness. You have faults that are at one point one singular fault and then split in two faults. You have splinter faults. In other data sets, you can see relay ramps, or you can see real stress structures, and that are all very significant indications that tell you something about the stress state, tell you something about the sealing quality of a fault, that you basically filter out when you interpret a manual interpretation of a single fault plane. So that's the value of it. Another value is that it's, once you have invested a certain amount of time getting to know the workflow, it's a relative quick thing to create. I think that you can make a good seismic attribute for fault detection in like 3-4 hours. That's a morning work. Compare that with the amount of work you have to do for a complete manual interpretation. But in the end, I still think that it's a hybrid solution. You generally want to make a seismic attribute for fault detection, and partly you want to use that for a manual interpretation, which will speed up by having this information readily available. One thing I would like to promote is a holistic approach, and I think a lot of people go wrong there. They they see the software and they go button clicking and they stop thinking at all. And in a holistic approach, I always promote to just get a coffee, put your feet on the desk, and think about 5 minutes what you really want. Make a final objective. And then going through the workflow, plan and QC against that final objective. So for every step, think about what is my problem getting from here to my final objective. What's holding me back? What methods do I have to overcome to that problem? What method is best? Then apply it. If you have applied it, check back. Did the method indeed do what I intended to do? And for that, you really have to understand the step that you have to apply. So you have to go through true understanding. And if your results are unexpectedly bad, then go back. Why did it work? If it's very good, you also have like a difference between anticipation and observation. Why did it work better than you anticipate? So that's a learning process. Then the first thing is state and final objective, and that's why I want to do this in the light of fault detection. Then you also have to switch between look detailed and look large scale on all levels. That means that you have to QC on small scale level, on large scale level. It means that you have to interpret on small details, but also on large scale systems. But it also has to mean like that in the workflow you have to switch between high level considerations, which method do I want to choose, and then detailed considerations like how do I parameterize a particular attribute. And then finally, draw in other kinds of data. Already in the processing stage, think about seismic quality. Is the seismic quality good enough? What kind of typical problems do I have? Migration smileys. Can I do something like an additional migration to get them out of there? In the interpretation, you can increase the value of a map incredibly if you integrate it with information like tectonic history, production data. Are two wells communicating, or is there a sealing fault in between? And if there are sealing faults and leaking faults, do the sealing faults have like other orientations than the leaking faults, etc., etc. So you can leverage the value of this data by a truly integrated geological interpretation. So think broadly there. Also, I want to promote a systematic workflow. That is what we're trying to do here. Not always we achieve to get it this neatly, but I would encourage to first go over data preconditioning step, look at the data. Can I make the seismic data look better for the particular final objective I have? Then work on the attribute itself, or the neural network for that matter. Yeah, that's kind of the same workflow. Then if you have a result, go to attribute enhancement. Do I see still some noise in the attribute image? Can I remove that noise? Can I make it visually more pleasant? And then go to interpretation. Work with your geologist if you're a geophysicist. Think about it. And with every step, if you're not satisfied or if something is unexpected, then you can look back to the previous thing. In the attribute enhancement step, I might discover something that I think I need to change in the data preconditioning. So I might have to look back a few times to get to an optimum thing. Of course, if you want to do it really perfect, you spend days on it. But there's a happy middle between just pushing like 3 buttons and having that as your result and working 10 days. There's a happy middle, like learning a little bit about your data and looping a few times back to get the results better. If you want to do such quality control, do it like with some objectives in mind, like some qualities that you want your data to have. One thing, if I do fault mapping, I want to know, is every discontinuity or every attribute anomaly I see indeed a fault? It might not be. In this case, I have a meandering channel, very obviously. That's not a fault. If I see that, I can work on each of the steps to minimize that, or I can accept it to be like that and just know that it's there. In this case, it would not be much of a problem because every geologist would recognize this as a meandering channel. But if I have linear channels, it would be more of a pitfall in interpretation. But that is the second advantage of the quality control process. You get to know your data and you get to know your pitfalls. So it's also an interrogation process of your data, getting to know your data better. So that's one thing. Is there a uniqueness in the meaning of an attribute? The second thing is completeness. Does the discontinuity attribute map all my faults? Because that is sometimes what people assume. If I make that attribute that say, well, there's a fault, and if I don't have an anomaly, there necessarily is not a fault at all. Well, that's not true. I mean, we can all agree there's a fault plane here, there's a fault plane here. But you see at certain locations, here and here and here, the reflector is for some reason continuous there. So this continuity attribute would not have an anomaly right there, and you would actually get a discontinuous fault plane in your attribute expression. Again, you might work it, you might also not be able to do anything about it, but at least you should know that that is a feature of your quality of your attribute. So you can take it in account when you look at it and you interpret your attribute. Because you're never going to have 100% uniqueness, you're never going to have 100% completeness, or very rarely. Then the final criteria I work with is you give this to humans to interpret. You have to have a visual, attractive solution. They have to be able to visually understand what it is. That means there should be a good contrast between what's anomalous, what's signal, and what is background. And maybe you can work with a color scale to indicate confidence, where you're very certain that an anomaly is a signal and where you have less confidence in the results. So that is a third additional consideration. Then finally, and that is maybe the most important step, because I see that so often once people get in front of a software program, they start pushing all kinds of buttons, but they stop thinking at all. It's very important to, for each of the steps, preconditioning, parameterizing the attributes, image enhancement, that you have a good understanding of what the steps do, because only then you can anticipate what the step should do, and if it does something else, if you get an unexpected result, you can loop back and try to find out why that is and get to a higher level of understanding. Use the QC to get to know your data. The QC will help you to get a better result in attribute values, but it also is a process of getting your hands dirty, similar with manual interpretation, and get to know your data. Use common sense. I will show in the course of this application presentation a few instances where just common sense thinking will get you from a very bad result to a very good result. And this is really the level of thinking that you would have as a high school person. But often when you just start pushing buttons, you stop thinking at all, and that is very risky. And that is maybe the 3 points I make here summarized. Keep thinking about what you're doing and avoid just pushing buttons, going like in software mode from one step to another step to another step without actually understanding what you're doing. So that were some general considerations. And now I would like to zoom in a little bit on discontinuity attributes and other approaches. Actually, I would like to start with mentioning some other approaches. Then some criteria, what method to choose. So here I do the high level thinking, the large scale thinking about do I want to use discontinuity attributes for this problem or not. And then I want to zoom in a little bit about the range of discontinuity attributes we have and say something about that. So other approaches fall into two categories. One is using other attributes. Mainly curvature attributes are very good for highlighting faulting too, especially in those situations I mentioned earlier where discontinuity fails. It's often because you either have like very small faults, the dip slip of the fault is very small compared to the seismic wavelength, or you have situations where you actually have the continuous reflectors. But in those situations you often have that the reflectors show considerable amount of bending, and then the curvature attribute, which is a measure of the bending, can actually map the fault planes pretty good. Now there's an important difference between discontinuity and curvature. Discontinuity maps the fault plane at a point of discontinuity in the middle, while the curvature has two opposite anomalies on either side of the fault. That's very important if you go, for example, to the next step, multi-attribute methods. If you want to combine a discontinuity attribute and a curvature attribute, you have to realize that they're not spatially aligned. You have to do an extra step to get the anomaly of the curvatures aligned with the anomaly of the discontinuity. And that's why if people try to combine them in a multi-attribute approach, they often get better results because they don't think about it. And that's one of the common sense thinking that you should have in your process. If you do such an additional step, you have to think logically, are the two attributes that I combine actually giving anomalies at the same place or at like different places? And if so, if there are different places, what can I do about it? In the end, it's not a very complicated problem to correct for that, but you have to be aware of that. So the other approach you could take is actually combine multiple attributes or the same attributes with multiple parameterizations and multi-attribute methods. And that can be something very simple. It can be an arithmetic combination or a simple statistical operation such as an addition or a multiplication or taking a maximum of two attributes. It can become a little bit more complicated using cross-plotting, for example, cross-plotting curvature and discontinuity, and then seeing which or highlighting fault step both have discontinuity and curvature values. And again, then you have to take that step that you realign the two attributes that they occur, the anomalies occur at the same place. Or if you have even more difficult situations, you can revert back to neural networks where you can have 5 or 10 attributes as an input. You interpret first the number of faults manually, then the neural network learns from your interpretation and makes an automated interpretation based on 5 or 10 attributes. So before you start making a fault image with a discontinuity attribute, you might actually sit back for a few minutes and think, is this really the best method? Mostly it is. 90% of the time we can use a discontinuity attribute for fault mapping. Sometimes you just want to use a curvature type attribute if your faulting is characterized by bending mainly rather than discontinuities. But that's quite rare. More common is that you want to recombine maybe a discontinuity attribute with two parameterizations, a long window and a small window, or a discontinuity type attribute and a curvature type attribute, and use cross-plotting or a mathematical recombination. I would say that's the other 10% of more difficult cases. And then in very rare cases, when you have very difficult problems, you might want to switch to a neural network approach. But the bulk of the fault mapping you can do with the discontinuity type attribute, and that's why we choose that method here. So in literature and in different software products, there are a number of different discontinuity attributes under different names available: coherency, variance, semblance, in OpendTect, Similarity, and there are some others too. In my experience, both from comparisons I have seen as well as literature, I would say most methods give essentially the same results. There are some differences and some differences in details. I will mention that later. That can be essential, but it's not a day and night difference between the methods. In my mind, most advantage in improving attributes here can be taken by careful preconditioning and post-attribute image enhancement, by thinking a moment about attribute parameterization, and if necessary, combining a discontinuity attribute with a curvature attribute if a discontinuity attribute alone does not give the satisfactory answer. So here we go through that workflow I'm promoting, and just as a little reminder, first we're going to talk about data preconditioning, then how to calculate the attribute, and then the attribute enhancement, and then a small example for interpretation. So why do you do preconditioning? First and foremost, to remove acquisition and processing artifacts, spike, acquisition footprints, migration smileys, that sort of stuff. Also, if you have small stratigraphic features that are not faults, you might remove them with data preconditioning. On the other hand, you can also try to reserve and enhance certain features in the seismic data using advanced filters, and that would be already more image enhancement rather than filtering. So internally, and there are other methods available in literature, and I will make sure that we send you the references to the other methods too, but internally we use three methods essentially. To remove noise, we use the dip-steered medium filter. To enhance resolution and with that fault visibility, we use Seismic spectral bluing. And to enhance contrast, we use the fault enhancement filter. And I will quickly go into each of those methods. The first one I will actually show live in the software, dip-steered medium filter, how to make one and what considerations to take with them. So let me go out here, bring OpendTect up, and add a line here with the seismic data. Oh, this is actually quite nice. You see that the seismic data is quite good, but there's some kind of striping in between there, and this is actually the fault system that we will start focusing on. And this feels like a little bit like a cooking show. I have prepared a lot of ingredients already, so I already have an attribute set ready, dip-steered filters, and I will show some results here. On the first layer, I will do a dip-steered medium filter. You make it in the volume statistics. Input is the seismic data. Time gate is 0, 0. You have a flat operator. I call it dip-steered medium filter 1 because there's a step out 1. Output statistic is median. The median has the big advantage that it's actually step preserving. That means if there's a singular spike, it will remove it. But if there's a step change, like with a fault, it will have to remain the step intact, contrary to an I-average filter. That's for fault detection. You should always use median filter, not averaging filters, and I actually will show the difference there. So here I did the dip-steered medium filter, applied it with an offset of 1, and you see that there's already quite some improvement Here you see that some of the striping is removed. I can also do the same for a dip-stirred medium filter with step out 2. I put it on an additional layer, and you see that there is maybe some more improvement. And let's look at it also in another color scale. That's often useful to switch between color scales because they emphasize different things. You also see that there might be some removal of stratigraphic features there, but that is not a problem as we're focusing on fault detection anyway. Also, we'll do a comparison with an average filter with the same parameterization. So there's step out 2, but the only difference here is that the output statistic of my filter operator is an average rather than a median. So let's apply that, and let's have the same kind of color scale. And it's not a big difference, but you see that at faults you just have a little bit more connectivity when you have applied an averaging filter, and that will make your discontinuity attribute just a little bit lower quality. That's why you always should use the median attribute. And finally, what I always do if I make these kind of filters, I want to see what's removed. So I make a residue attribute, which is quite simple. I use the mathematics attribute. I say, give me the original, the input of the filter, the seismic data, minus the filter, and subtract them from each other. We'll get an image that looks like this, and that's pretty random noise, maybe some stratigraphic features that are included in there, but this is pretty much an okay removal for me. So as I already mentioned, what you finally want to do is also understand the effect of a preconditioning on the final objective, mapping faults. So I do want to have a quick look at how this filtering step actually affects my final output. So I'm going to make it small or smaller. I'm messing up here. I'm going to trying to make a small time window here, or time slice here. There it goes. And let's put it at 1660. And cancel that for now. So you see that's just on the top of that fault system. And I will go back to the attribute engine actually to show you what I'm going to compare. I have two similarity attributes defined here, and I will go into the details of that later. But the input of the first similarity attribute is the seismic data, and I combine them in a mathematics attribute. And then the second one, the input is the dip-stirred medium filter I just created. Combine them again in an overall mathematics attribute, combining multiple directions. So we'll apply one to the lower layer of this slice, and it will take a short moment to calculate. Actually, I will make the window even a little bit smaller to speed this up. Yeah, cancel that and recalculate it, and it should go a little bit quicker now. This is often the time that I actually run to the coffee machine to get some more coffee. just fits in this time period. And here's a typical result. You see this like haze of like little stipples over there, and that is one thing we're trying to remove here. That is caused by that striping you saw earlier in the data. And here I go with the preconditioned data doing the same thing. And there you got it. So let's zoom in on a few things here. Let's OK that window. And let's have a closer look here. That's a pretty significant difference. You see that there's a lot less background noise here, that some of the faults have collapsed in a nice image of the fault in here that was not visible on the similarity attribute that was run on the initial data, but is present on the similarity attribute that's run on the preconditioned data. Also, if I go to this area here, I see that first I didn't see anything in there, and now I start seeing some coherent features in there. So that preconditioning step is very important. Also, what I do see here doesn't look like faulting, and that's one of the things. If I see something like that, I become curious. In this case, I might add a cross line and have a look at the cross line. Often you do this kind of interpretations by switching between a top view and a section view to have a little investigation what I'm actually seeing. And if I look at this here, these are primarily sedimentary features that I see here in my discontinuity attribute. Now, of course, I can try to work them away, but that might be very difficult, and it's not that bad that they're in there, but this kind of curiosity, having a look at it, will make you aware of what the data is actually telling you. So that is very important to do as part of your QC process. So that is a little demonstration of one of the preconditioning steps, and probably the most essential preconditioning steps, especially even if your data looks kind of okay. You often get a lot of mileage at applying a dip-steered medium filter, removing some noise, removing some acquisition footprint. So let me talk about two of the other preconditioning steps we often do. One is spectral bluing. I just had a conversation with a colleague of mine who was working North Sea data, where mapping often very subtly present faults is very important for reservoir evaluation, reservoir characterization, because you're dealing with reservoir compartmentalization there. You want to know where those small faults are, and they use this spectral bluing algorithm all the time. It's originally a BP idea. But this colleague works from other company, and they routinely apply it to the data. It's based on the fact that if you have well logs, they have self-similarity. That is, if you look at 100-meter well log or 10-meter well log or 1-meter well log, and you look at the acoustic impedance well log, you wouldn't be able to tell how long that well log actually is, if it's 100 meter or 10 meter or 1 meter. The variations in there look the same. So that's kind of a fractal behavior, and that leads to that if you make a frequency spectrum of a well log, that you have an increase in frequency in the amplitudes of your frequency spectrum towards the high frequencies. That's opposite to the behavior you see in your seismic data, which is either peaked or quite flat with some nodal behavior. Of course, in the seismic data, you have on the low end and the high end flat behavior, which is basically your noise level. We don't want to deal with the noise level part of it. here, but we want to deal with the signal level part of the seismic spectrum, and we want it to have the same shape as the reflectivity spectrum in your well logs, because only then you have a true reflectivity image in your seismic data. So the spectral bluing algorithm actually measures this slope, measures the increase in frequency in the well logs, and makes an operator that will apply the same kind of slope to the signal part of the seismic frequency. So it's basically the same idea of spectral whitening, except that it's not based on the flawed assumption that your geological spectrum is white, but on the true assumption or the true fact that your geological spectrum is actually blue and increasing amplitudes with frequency. And this is the typical result you get with that. This is a reservoir here, and the reservoir has very subtle faulting in it. For example, in this region, this is the before image, this is the after blued image, and you see that the faulting is much more obvious. But for example, here and here, there are also two faults that you pick out much easier on this image, on the blued image, than on the original data. So especially if you deal with quite low dip slip faulting, that is very critical for reservoir engineering. This is a step that we would always include in the preconditioning, provided we have well logs available. But if you're in a reservoir characterization kind of mode, you often have enough wells drilled already. Then the final filter we often do is the fault enhancement filter. It's basically based on a filter that actually enhances, sharpens edges, which makes if you have like fuzzy fault zones, it makes the appearance of the fault zone a little bit better. However, if you apply this diffusion filter, that sharpening filter, just everywhere, it will create a lot of edges that are not related to faulting. So we do something smarter. We make a conditional filter. We first going to make inference where we have faults and where we don't have faults. In 90% of the data where we do not have faults, we apply that same median dip filter I demonstrated earlier, the dip-stirred median filter. It will still preserve like faults or steps if you have one. So if you make an error in the conditioning, in the condition step, it's not bad. And then in the 10% of the data that's near fault, we'll move seismic amplitudes from farther from the fault towards the fault, from both directions. And that has the effect that a fuzzy zone that's not imaged well around the fault disappears and is replaced by actual good amplitudes. And since they're moved from each side, they create a pretty sharp edge around the fault. This is the effect of that, and this is actually the effect of that that's already on a pretty good data set. But you still see that when you have faulting, especially in a zone like here, they have collapsed to a nice, straight, crisp image. And especially if you have a lot of these fuzzy zones, like here again, it's a good idea to apply this filter. If you already have good quality seismic data where the faults are quite sharp, it's not necessary. So these are three typical steps that we in-house do in the preconditioning. So if you have preconditioned your data, your next is to work actually with the discontinuity attribute. And in our case, in OpendTect, that's the similarity attribute. So I will go over the definition of that, go over some details of the similarity attribute, actually explaining how it works internally, because I think that's very important to understand how things actually work. And then the role of dip steering and preconditioning of the dip steering volume. That's again an essential step, will give you a huge increase in results if you do that right. And then run over some main parameters of the similarity attribute. definition of seismic discontinuity, mostly it's defined as a lateral discontinuity in local waveform between two seismic traces. So you're going to look like a few milliseconds up, a few milliseconds down, say 5, 10, 20 milliseconds up and down. And if there's a lateral discontinuity between waveform, it's indicating that the seismic reflector is discontinuous, and biological appearance, it means that your strata, your geological strata are discontinuous at that location, which could mean a fault or an incision, erosion. Then how to calculate that? Most discontinuity attributes, including our own, use some measures from vector algebra. Coherency used the dot product, similarity used the Euclidean distance, combined with statistical operators such as taking maximum or minimum from different measurements, or as the variance attribute, it's a statistical operator per definition. So that are typical ways to quantify amount of discontinuity you have. So let's focus in how we do that in OpendTect with Similarity. What we do is we run a calculation that goes trace by trace, and every trace the evaluation point goes in a running fashion down the trace. And at that evaluation point we're going to calculate the similarity between local waveform between trace pairs. We can do that for multiple trace pairs, but we do it first for each trace pair separately. So at the evaluation point we take a time up, a time down. We interpret the trace as a vector. Here the samples we extract we interpret as a vector, and then we take the Euclidean distance between the two trace segments. Then we divide by a normalization term to make sure that this range is actually between 0 and 1, and then we do a 1 minus to actually make sure that when your seismic data is absolute continuous, you output a 1. When it's absolute discontinuous, like the two waveforms are orthogonal to each other, their mirror image, you get the output that's 0. Also, it's nice to notice a small difference between two attributes. The coherency attribute actually uses a dot product, which looks much more to the wave shape. If the wave shape is the same, but the amplitudes are different, so they're basically scaled versions of each other, the coherency attribute will still output continuity, while if a similarity encounters the same wave shape but different amplitudes, for example, if you enter a reservoir with hydrocarbons in it and the amplitude changes, it will actually output a lower than 1 value. It's sensitive both to wave shape changes as wave amplitude changes. And therefore you see often somewhat more variation on the similarity display as on the coherency display. There's also another reason for that, but that's one of the reasons that you have small differences, but those are not essential differences. So how does it work with the multiple pairs? Typically we try to have one of the waveforms of the trace pairs at the evaluation trace, at the center trace, and we'll have a second trace that for the different evaluations goes around the center trace. So you have a relative position of 1, 1, 0, 1, minus 1, 1, and goes around, makes a comparison between those two waveforms, and then like those two waveforms. So typically, if you do it for the perpendicular directions, you would have 4 comparisons. If you include the diagonal directions, you typically end up with 8 different trace pairs you do a similarity measurement on. And then you recombine it with a statistical measurement. Typically, we take the minimum or the average of them. Then the final thing we use is dip steering. You always have to correct for the dipping reflectors. If you just use a straight extraction, as done is in this part of the similarity display, you're going to make errors, because if you do a straight extraction and you move to the left, you end actually up in a different part of the seismic wave train, even if your seismic reflector is completely continuous. So you have to correct for your dipping reflectors, because otherwise you will get artificially lower similarity measurements because you move out of the seismic reflector plane. That is why we make a dip steering volume in advance, and we correct the extraction of neighboring points for the dip of the seismic reflectors. And it works even if the reflector is severely curved, because we don't use a central dip, we use a dip for every pathway separately. But it's very important there to realize what you do. A dip steering that you create will output a local dip to begin with. And the local dip can actually contain data that will guide it over a fault and end up at the same part of the seismic wave train. In other words, the dip corrects for the dip slip in the fault, and that is especially severe if you have small dip slip faults, or if you have amount of curvature around the fault. What you should do there to correct that is apply a lateral, median, or lateral averaging filter that removes the localized information around the fault. You see that these extreme values that are associated with the dips of the faults are very localized. So if you put a filter with a large enough aperture here, it will smooth it out. And with that, if you do an extraction near a fault, it will just use the regional dip of the strata either there or the strata there, and it will take a trace there and a trace there, and the two traces in the trace pair will be very dissimilar. On the other hand, if you're in just a fault block and dipping fault block, that filtering operation won't do much. You will still get a correct similarity measurement, because the subregional dip is good enough there to guide the trace pairs to the correct position on the seismic reflector. That's an essential step, and I will show you the difference. This is a similarity attribute created with detailed steering, so without any lateral filtering. And this is a similarity attribute created with background steering. And you see at some places like here and here and here, the similarity attribute with the detailed steering doesn't pick up in discontinuity because the dip steering corrected for the discontinuity. Well, if you do it correctly, you just see quite clear faults there. In other locations, the quality of the similarity attribute is just not as high as when you do it with the background steering. So this is together with a dip step medium filter as a preconditioning step. The preconditioning of the steering cube is essential. And how to create these background steering cubes, there's an excellent how-to for that, and we will include that in the email with resources that we will send you after the webinar. And then there's some other parameterizations in the similarity attributes, such as the spatial distribution of traces. I already showed you our default situation where we have one trace in the center and then move the other traces around it. The time window, that's very important, because there you try to outtune discontinuities with small vertical extent, and those are often due to stratigraphic features. However, on the other hand, you're going to have smearing if you use large vertical windows, so you're always trying to compromise there, and you have to do some research there or some testing to find the optimum. I actually will show that. And then the output statistic, we always use the minimum average, but I will actually show you in OpendTect what happens if you use a maximum there, and why that's not a good idea. So we'll switch to OpendTect real quick and show you some typical testing of the similarity attribute I often do. So let me clean up here. Oh yeah, and that's one additional remark I forgot earlier to say. if you look at discontinuities, in 99% of the time it's a good idea to look at it in grayscales with the anomalies in the dark colors and the background in the light colors, or another unilateral color display. So if your default color scale is actually your Seismics, make sure you switch that to grayscales before you start quality control or interpretation of your similarity attributes. So let's have a look at this. I will add some layers here to this display, and then here I already prepared some attributes, all with that dip-stirred medium filter as input. These one have, let me actually show you how I came up to that number, and that's another example of common sense thinking. When you're going to think about time windows for your similarity attribute, you want to normalize that to your seismic frequencies or to your seismic wavelength. So what I always do is I take the measurement tool here, and I'm going to take from here to here, zero crossing, then over peak, then over trough, and I'm going to read how many milliseconds that is. That is 20. Let's do it for another one here. That's also around 20. So your wavelength here is approximately 20 milliseconds. When I start testing, I try to normalize my testing parameters to that wavelength. So usually what I do is to half a wavelength, one wavelength, and twice the wavelength, and see how those different attribute parameterizations look on typically a section view. That's most important, because here I work with continuity, smearing, and you see that best on a section view. So I have them ready here. This one is made with minus 12 to 12 milliseconds, and I take them in two directions. I only do the perpendicular directions here, not the diagonals, and then I recombine them in a mathematics attribute, taking all four directions. And this is how that looks. Then I have the same thing for minus 6 to 6, so that's half a wavelength approximately. And then I have done the same for plus minus 24, which is twice a wavelength. And let's go between the extremes, the minus 24 to the plus minus 24 and the plus minus 6 milliseconds, just to see what is the difference. You see that the continuity of the 24 one is much larger. For example, here I have a big gap sitting in the minus 6.6 that's really fragmented, but it comes at a cost. It comes at the cost of vertical smearing of the seismic attribute. Another effect that you see is that sometimes you see these like little dots in the middle of nowhere. Often these are due to stratigraphic features. You can always check what's causing what by using the transparency. So I right click on the attribute layer, and I change transparency, and I can actually see what's causing what. And here the example of that is typically it's a straight determination, and those straight determinations also cause like little anomalies. These are filtered out very much if you use the minus 24 to 24, so you have far less interference of stratigraphic noise on your fault image. So let's do a comparison between the minus 12.12 and the 24.24. So here I still see some discontinuity. I still see some like those little dots that are away here, but I have a lot more smearing here. And I looked at this yesterday, kind of like both, but I kind of didn't like both. The simple solution of that is to just take the parameter values of both instances and average them. So what I did eventually is I created the similarity attribute with plus minus 80 milliseconds, which is just between the 24 and the 12 in. And I'm doing something wrong here. And I created that, I tested that, and I kind of like that as my ideal compromise. So one more time actually use the transparency to see if this indeed images my fault. You see there's still a little bit of smearing. Here it goes a little bit too high up, but I can live with that. And once I'm satisfied with that attribute, I went to processing, create seismic output attribute, and I process that as a stored volume. So then I can load it here on my slices, and in this case I did it with an averaging operator. I actually changed it already, but you can also do it with the maximum operator, and just to see what is the effect of that parameter, I will calculate it real quick. So I have 4 trace pairs. In the image you see now, I combined the 4 trace pairs using an averaging, and I will do it with the maximum. And you see that image is far less good quality. So that's another pitfall. The statistical operator should always be a minimum or an averaging for good results. So I realize I'm already talking for an hour, so I'm going to try to hurry up a little bit, but I have some material to go. Back to the slide. What I want to do now is talk a little bit about attribute or image enhancement. Once you created the similarity attribute, you processed it as a volume, you often still have like, hey, this could be a little bit crisper, or I have some noise still, and that is what you address in the subsequent attribute or image enhancement step. The objective is to remove noise and add maybe some missing data through automated filters, etc. So there are a few steps that I'm going to treat here: removing stratigraphically oriented noise, rich enhancement filter, a trick that you can use to directional decompose your fault sets, and then actually derive steering from your faulting and applying a structure-oriented filter to your faulting, which can improve your results significantly. I will demo this, and I will demo 2 steps. Remove stratigraphical oriented noise. Though it's not severe, I will just show an option how you can do that. And stratigraphically oriented noise is basically similarity values that are anomalous but are related to either stratigraphy, little channels, etc., or some noisy data, for example, low amplitude layer or zero crossing. And then we will do an adaptive second order derivative filter. Second order derivative filter is a filter that you use to make things sharper, crisper, and it's based on calculating the second derivative in multiple directions, all in a lateral sense, so in inline direction, a cross-line direction, or along a diagonal. And if you do that, it will emphasize actually where the point where you have your peak in your fault. And we created filter from scratch in OpendTect. The equation for that, I do want to mention that, is the second order derivative is numerically expressed as shifting one sample up or in front, shifting one sample back or downward, depending on what you're doing, adding those 2 shifted samples up, and then subtracting them twice by the middle sample. And if you do them in multiple directions, inline, cross-line, diagonals, you can bet that one of the directions is approximately perpendicular to the fault, and it won't see the fault at all. And then you have probably another direction that's, there's one direction that's probably parallel or approximately parallel to the fault, and it won't show the fault at all, see the fault at all, so that direction doesn't work. Then you have probably a direction that's perpendicular to the fault and crosses the fault. That one sees the fault optimally. It just goes straight over the fault, and there the derivative filter will have the optimal signal. So the second step is, of those multiple directions, we select the best directions. So let me show you how that looks in OpendTect. Here it is, and I will have to switch data sets here, and I get a little error message here. Let's see if I do it okay, or if it still works. One thing I'm going to address first is stratigraphically oriented noise. Let's make sure we look at the right thing. What you see here, these things, and they're not very obvious here, is stratigraphically oriented noise. These are the bands that actually go with the seismic strata, and they can be caused by little channels, by low amplitude data, and in some applications sometimes they are very severe and you want to remove them. It's a very simple trick to remove them. Here we use a stratigraphically noise filter. I give it a very fancy name, but the only thing what it does is actually it calculates the median operator over a little time filter, and the time filter should be either one sample up or down or two samples up and down. If you do more, it starts affecting the data too much. And again, I use the median operator because it's step preserving. It will remove the spikes due to this noise, but it will actually keep the steps on the top and the bottom of your discontinuity intact. So let's see how that looks. Make sure I have my transparency off. And you see between the two there's far less of this stuff going on after I did that stratigraphical noise filter. It's not a day and night thing. This is actually a pretty insignificant step, but it can be very useful in some data sets where this problem is much larger than in this particular data set. So I thought it was good to show. So now let's go over to building the rich enhancement filter. I will first add again some layers to my time slice. Here, this is the similarity, the original similarity that we use as an input. And then what I do here, I use my reference shift attribute to move things around to the left diagonal up, to the -1 inline. I move things laterally. And then I use my mathematics attribute to make a set of equations that actually use the shifted versions of my attribute to recreate the numerical expression for the second derivative. So here I go in the inline direction, I go one inline position back, I go one inline position up, I add those up, and then I do twice minus the center position. And let's have a look how that looks. Let's put it on. And this is work for a moment to switch to a seismic color scale. And what you see here is just taking the second derivative on one direction, and it does exactly what I expect. It gives large positive values at the center of a fault, and it gives two negative, smaller negative side lobes on each side. That's not something to worry about. Actually, when we do our selection of best direction step, those side lobes will disappear as a happy byproduct of the statistical operator. So we will do this derivative operation in all directions: the inline direction, one diagonal direction, the second diagonal direction, and a crossline direction. So I make the mathematical equation 4 times, and then I'm going to combine them. I'm going to select the direction with the best signal, so I'm going to take the maximum there. And because I take the maximum, those little negative side lobes that appear on the side of a fault will disappear automatically, because taking the maximum value will actually remove negative side lobes. So let's apply that. And let's put it on. And here my default color scale is it has the wrong polarity, because here the good values are actually, or the anomalous values are actually positive. So I go back to my original grayscales. Other thing I have to realize, there are still, because of the negative side lobes, some negative values in there, but I'm completely not interested in them. So I have to adjust the color scale a little bit. I make it slightly positive, and that's one of those like things. Keep thinking, keep using some common sense. There are not supposed to be any negative values in this display that are meaningful, so you can just wipe them out by your color scale. And then you get your optimized image, and let's compare that with the original Similarity. You see that all the faults are a lot crisper now than in the original Similarity. You see that some faults that are first kind of like diminished, not very obvious, come out more to the foreground. So this rich enhancement filter, the view, the output product of that, is what a lot of interpreters actually prefer to see to make their fault interpretation on. And again, looking at this, here I see some things that doesn't look to me as faulting necessarily. So that would be again one of those things where I get a little bit curious. What is this? It's not faulting. That is some sedimentary stuff that goes up and down there. Actually, let me go to the dip steered medium filter. So I keep thinking about all steps. That is actually the gap between this little and this little channel. I keep thinking about my seismic data. What do I see? And if I see something curious, I go in and I investigate my data, and I get to learn by data. So this is some sedimentary feature, and I want to check how it moves there, if that's still sedimentary or if that are fault systems. Then I have different fault systems here, 2 directions that I see very clearly. I see a lot of detail on this. So that is kind of the end product you want to work towards doing. So I've been now working on this for about an hour, and I've moved myself to a very rich, very informative display of seismic discontinuities for fault interpretation. So that's about time investment that you have to do, contrary to manual interpretation, which is a lot more work. So here are some advanced tricks that you actually can do also using that same kind of second derivative algorithm, but combining it with some integration and doing it directional. I can actually split a fault display in faults oriented in different directions, and I can, for example, displaying them in black for one direction and in red for the other direction. I can see how their cross-cutting relationships are, which fault direction cross-cuts which other fault direction. Or I can display them separately. I've decomposed this image in this direction and this direction. I see that for the direction that goes from southeast to northwest, I have much more density here. While in the other direction, I have much more density here. Also, I start seeing lineaments here that are not that obvious from this data because I see too much data, I see too much directions that have too much cross-cutting faults here. But here you can actually see this might be very well one fault trend cross-cutted by some other faults in the other direction. This might be well one fault trend. This might be very well one fault trend. I'm happy to discuss these kind of advanced algorithms separately with you, but you can do additional tricks to make it visually more pleasant to interpret these data in addition. Also, an advanced algorithm to get even better results is creating dips from your seismic data, from your fault data, from your discontinuity data. That's involved, that is not a trivial process, but once you're here and you have that dip volume, you can do all kinds of advanced things with your similarity attribute. One thing you can do is you can apply a dip steer filter along your fault plane. For example, an average or a medium filter. What you see there is that you remove your staircase behavior. It's often a problem with similarity attributes that staircase behavior is real. I mean, you see it in the seismic data, but it's not geological perceptual how you think about faults. A fault is not a staircase. Well, this filter removes that more or less. Also removes discontinuities, little places in your attribute where the fault is not imaged well, and fills it up and makes it continuous. So for a geologist, this image might be actually more pleasant to look at. In addition, if you have automated algorithms that requires faults to be watertight, it's a good idea to have this operation done. And then, for example, here you have an artifact that's discontinuity artifact that's relative flat. Well, faults are supposed to have a high dip, so you can make a dip conditional filter and say every feature that has a dip too low, I remove it. And this is one of those advanced applications where you require watertight faults. Basically, we use auto tracker here, but we say stop if you come across an attribute value that's so anomalous that it indicates a fault. So with that, you make the interpretation separate for each fault block. So you have to put a seed in each fault block. But it's very important to have good fault continuity here, because if you have a gap in your faults, what will happen is that once the auto tracker reaches the fault, it will jump through the gap and it will start tracking at the wrong level in the next fault block. So creating a good fault attribute, discontinuity attribute, is very important if you're going to incorporate them in automated algorithms downstream. Then real quick, a little bit about application. We already see that the value of discontinuity attribute is that in an hour or 2 hours work you can make a complete, very rich map of fault-related discontinuities everywhere. You can glean all kinds of details, fault splinters, redo structures, etc. The value of that work can be enhanced tremendously if you're doing integrated geological interpretation. So you're going to think about tectonic history, production data, etc., etc. And as everybody can understand, such a seismic attribute display, it's a good tool for integrated teams and workflows. So this is a very quick example where we look at a fault display that images two sets of faults, one in the northeast southwest direction and one in the northwest southeast direction. We know the current, the modern day stress state, which is approximately perpendicular to one fault plane and perpendicular to another fault plane. What we see then is we made a guesstimate attribute that actually measures leakage through the fault system, vertical leakage through the fault system. And we see that some fault sets, some fault directions are actually resisting vertical fault leakage, and then other fault sets are actually allowing vertical fault leakage. So having that display, you want maybe to combine this with production data. Those production data mainly occur here because I have better sealing, or do they mainly occur there maybe because I have an efficient charge mechanism here, and I don't have an efficient charge mechanism here. So with that kind of reasoning, you can leverage the value of such an attribute display even more and make them a part of a truly integrated geological interpretation. So here I'm at the end. What I did is I gave you some general considerations and structure for creating attributes and neural network workflows. Overview of methods for preconditioning, attribute design, and attribute image enhancements, which are the big 3 steps in your workflow. Demonstrated some details of some steps, and then showed a final application about how to put this in a geological context. If anything you take back from this, I've been talking for a very long time, there are 3 points I would like you to remember. Be systematic, use a holistic approach with the final objective in mind, always QCing, and go systematically to data preconditioning, designing the actual attributes, and doing attribute enhancement. And read the papers, go through the how-tos, and really understand what you're doing in each step. That will give you much better results, avoid disappointments, and actually help you get to know the data. QC with the final objective in mind for uniqueness, completeness, and visual quality. And you're not going to achieve the 100% solution there. You're going to achieve maybe the 90% or the 95% solution if you put in a few hours work, which is much better at just pushing the buttons. And for the 5% that doesn't work, just using that QC process, interrogating the data will make you aware of the artifacts that are in the thing, the pitfalls you have to deal with. You can shoot an image of it, you can put it in a report, so if you give the volume to a colleague of you, he will be able to understand what the discontinuity attribute really means, if it only means faulting or if it means faulting in a mass transport systems, and then how he can recognize the faulting by putting an image of the faulting in there, and how he can recognize the mass transport systems. And that is also the last point, enhance the value of the attribute by including it in a proper integrated geological interpretation. Don't, like as a geophysicist, create a volume and then say, well, I have a volume now that is the discontinuities, but try to understand how it relates to geology, how can I interpret this in current day stress state, in pre and paleo stress states, if there have been changes of stress direction, did it create a new fault direction, or did it reactivate an old fault direction and created flower structures? And also the other way around, can I fill in some missing links in my geological understanding using the similarity attribute? So that brings me at the end of this presentation. Finally, I want to thank my colleagues, Renee for moderating, and Arnaud and Christopher for paneling. And I hope this was useful for you, and I hope you have some good questions left after this presentation. Thank you very much.
Well, thank you, Friso. We actually have had an active question session while you've been talking, so that's been very useful over here. But I would like to go ahead and open up the floor to people who would like to send in questions now, or who would like to raise their hand and ask their questions aloud and have Friso answer them. If you would prefer to be anonymous, then please just type your question into the questions pane, and I'll read them aloud anonymously for you. And actually, we did just have one come through. I'm going to send this to you, Friso, so that you can read it, but I'll read it aloud as well. So it asks, Could you show the different fault highlighting attributes, such as coherency, similarity, curvature, on top of each other so that we can see what different things they highlight, such as which one would you use for a specific task in your interpretation process?
Well, the problem, it's a good question, and I've done in the past some comparisons, especially with coherency. But I don't know. I'm reading the image, the question. Yeah. As far as the discontinuity product itself, coherency, semblance, etc. The problem is that they are in different software packages, and so direct comparison is often inhibited. So though I have done some in the past, and they essentially give the same results. The big difference is often in similarity and curvature, and there you can indeed overlay them. That's actually very good. But what I would do in those cases is both do some investigation on section views, how they look, as well as do some investigations on top view to see the differences that they highlight. Let me see. I can actually show you not in OpendTect, but oh shoot, in my desktop on another PowerPoint how you can overlay those. Desktop, travel, library, attributes. So further down here, I have indeed done some comparisons between curvature attributes and similarity attributes. And what I always do, and this might actually be included in this presentation, I'll always go back to section view, and I like to see what's happening in the section view to really QC the attribute. But then also, let me find them. You can make overlays, and I made here an overlay using different color scales of different attributes. Here I overlaid the similarity attribute together with the most negative curvature, and the most negative curvature I overlaid in that way with again a unipolar color scale, but I made the lower end of that color scale transparent, so the background value is transparent, and I only highlighted the anomalous values in green. And you can do it different ways. You could use this method. You can just use different color scales and use some transparent blending if you want, but I don't really recommend it. You could even use the red, green, blue color blending that's available in OpendTect. I hope that answers the question.
I will wait for a reply from the person who asked the question, but I believe it did, and Arno Hoek was actually going to add in on that, and it was going to be the red, green, blue, so you covered that as well.
Okay.
So, and yes, we just had a response come in that says, yes, thank you.
Yes, one visualization technique to remind when one wants to compare different attributes is RGB blending, especially when you have attributes that are normalized between 0 and 1. You can always overlay up to 3 attributes by putting one attribute in a given color range.
Okay, and also, we had somebody asking questions during the presentation that I think would be useful to the rest of the audience, and it was regarding 2D lines. If these could be applied to 2D lines, would it be in the same way? Would you have to consider other options? Would there be any considerations for that?
Yes, there are considerations for that. You can do this in 2D lines, though, like the whole geometry with the trace pairs gets a lot simpler because you can only go one direction in a 2D line. The rest would be, so you also wouldn't have any output statistics, but the rest of the time window you still would have to analyze. I guess it's a good way to make an image if you have a lot of faulting going on, or if you have a lot of smaller scale stratigraphic features there that you want to get a handle on. You don't want to interpret that manually. I mean, if you have 2 or 3 big faults on 2D data, it's not a lot of work to handle it manually, but if you have like a very information dense 2D line with a lot of small scale faulting, you still can do this. The obvious disadvantage is that you cannot map it on time slices. I did not mention it, but one of the reasons that you make actually a discontinuity attribute is that on time slices, when you just display the amplitudes, I mean, it's kind of non-informative. It's very hard to discern faults there. But when you slice, time slice or horizon slice to a discontinuity attribute, the similarity, you create an instantaneous map of your faulting at that level, and it's a very simple map. It has like low values for where there's a fault, and there's high values for when there's not a fault, and that you will not have when you use 2D data. So the added benefit is a little bit less. But if you want to map like very subtle faulting, etc., it still might be a good idea to do it.
Yes, and although the display to time slices is not available, if you have a dense set of 2D lines, it is possible to apply a line set attribute along a 3D interpretation. It will require you to grid the output attribute in order to have a decent display, but it is possible to apply 2D data along a 3D interpretation.
Right, thank you, Friso and Arnaud. And we had another question come in. Friso, I've sent this on to you, but it's asking what the best approach for removing a strong acquisition footprint is.
Well, that's a difficult question. One thing I have noticed is that sometimes when you use the medium filter and you have an acquisition footprint, you have kind of resonances between the medium operator and the acquisition footprint, and you can imagine that because the acquisition footprint is basically a bunch of steps, and as a medium filter is step preserving, it might in some cases actually leave the steps intact, and that's not what you want. So what I sometimes do is, but you have to be very careful with that, is apply an averaging filter to remove a strong acquisition footprint, and then I prefer, for example, if the acquisition footprint is only in one direction, which is only often the sailing direction, to have that filter only have an aperture in the direction that's perpendicular to the direction of the acquisition footprint. So I do not do any unnecessary smoothing. Another option is, but you would have to do that outside OpendTect, is to start working with eigenvector filters, which basically go over different levels and see what's the common vector, the common data values between all the levels, and then you can make an eigenvalue to composition. And then often the things that are present over a long time window will be having high eigenvalues. So if you filter those out, you will end up with a relatively clean image. That is not the technology that is enabled in OpendTect. Does that answer the question?
I'll wait for a response to see if that answered the question. And yes, that answered the question. So very good. Well, at this point, there are no other questions in the questions pane, so I'll give everybody a moment to, if you have a question that you were trying to type, please go ahead and send it in. But in the meantime, I would like to thank our participants once again. Thank you, all of our attendees who've been asking questions or just listening and learning. Thank you for joining us today. I'd like to thank our panelists, Christopher and Arnaud, and of course our presenter, Friso, has been very helpful today. And I would also like to mention next month's webinar, where we'll be teaching you, showing you things that are now available in version 4.2, which is on the website for download. Version 4.2 has a lot of new features and new workflows that go along with it, so we'll be showing you a lot of those new things next month. Such as trimming horizons at faults, creating faults from fault stick sets where you can draw them directly on the lines. So please do join us next month for that webinar. And we do have one more question here. The question is, are there any instantaneous implement? Let me forward this. Actually. Intentions. Oh, are there any intentions to implement factorial kriging to analyze and remove directional components?
I would like to forward the question to Christopher, as he is more aware of software development plans than I am.
Okay, Renee, could you just send me the question in written or read it?
Yes, and you will also need to turn up your volume. It's difficult to hear you.
Okay.
Okay. So the question again is, are there any intentions to implement factorial kriging to analyze and remove directional components?
I think that the kriging is one of these things that have been hovering over our software development team for quite a while, and I think it's just a matter of time until something is implemented. We had a kriging implemented in our older software, GDI, and I think it's well, I cannot give any time and date, but I would be surprised if it's not coming into OpendTect itself at some point. Now, we are currently working on a lot of things in OpendTect, especially with regards to the horizon cube. So obviously that has at least right now, much higher priority for us. But it's one of these things that, well, one good day it will certainly come.
All right. Well, thank you, Christopher. And yes, we also got a thank you from the person who asked the question. So if there are no other questions, then I would like to go ahead and say thank you once again to everybody who's attended and everybody who's been participating, asking questions and answering questions. If you have any more questions, then please just send them to us in an email. We'll be happy to talk with you about this in further detail. And be looking in your emails at the end of the week, where we'll send the link where it's posted online, as well as some of the additional materials that Friso described at the beginning. So thank you everybody for joining us, and we'll see you next month.